Whoa. Why is my hair so flat today?
Are you guys ever worried about a chair just spontaneously breaking?
Yeah.
Okay.
Jacqueline, do you like my background? Don't. Yes, you do.
Are you kidding me? For math, she gave me a D on the web work even though I got them all right. I think she put it in wrong.
Most likely.
And I'm just looking at this like, please man, don't do this to me.
Is it just me or does his mustache look
Was he
different?
here left or is he still late?
Is it just me or does his mustache look different?
We are all here. All right. Topic for today is universal gravitation. The activity for today would be doing the video lab. That's where you're throwing the ball. Basically, we've got a 2-meter, white 2-meter stick on the wall, kind of just behind this foam disinfectant applicator. And a little drawer just through the hallways full of like yellow softballs. So you can all take your turn throwing that. You can put your computer just on that first lab bench and point it this way. You should be able to get the whole flight of the ball. The main thing is, don't throw it too high. And then you're going to need the 2-meter stick to set the scale when you do the analysis. There's a fair amount to the analysis this time. So you want to make sure you get your data today, even though it's not due to a week from Saturday. It's going to take some time to do the analysis. But basically, in the frame, you have to tell it, this meter stick here, you click the ends, is 2 meters long. Now, in terms of your data, it's not terribly important that you've got it all the way to the floor, and maybe you clip the edge. But what's important to know is if you don't have the 2 full meters on that stick that you're clicking on, you better know it was like 1.7 or 1.8 or whatever. So if in your video you don't have the edge, figure out, and if you can't see it, the numbers are too small, then maybe you put some tape on the wall and do it again so you know, oh, that was like 1.75 meters or something, because that will affect the values you get if you shrink or expand the scale. Anyway, that's what's the plan, and since we have a retest on kinematics the next time I see you, which is Monday, if you haven't done your test corrections, maybe you want to just quick throw the ball, get your data. It should take like 2 minutes, maybe 5 if you do it 2 times. But hold off on the analysis. You'll have some time next week to do the analysis. And then get on to your test corrections. So I have your tests here. Don't be forgetting about the quest. We've got one due this Friday, free fall 1. We have one due next Monday, universal gravitation. We have one due the following Wednesday, free fall 2. And there may be one more that will be due on the weekend before you come back and have a test on gravitation a week from Monday. So that's the 13th. Oh, as a help, there are additional kinematics problems on Quest. I post that for practice. You don't have to do it. You're not scored on it. But that assignment exists, just as additional kinetics problems. And you can be doing that if you'd like some more practice. Questions for me? All right. Give me a minute to mark it. Well, you know what? I'll mark it in a minute. But we want to get started on this idea of universal gravitation. Now, what were we doing with gravitation last period? Last time we met.
You were using the 9.8 meters per second squared acceleration to find position.
Our little g, gravitational acceleration. And I'll say on Earth. And what things were we doing with it, Ron?
We were given an initial velocity. We could plot the position of an object over, like, if you're throwing it up.
Okay. We're doing basic kinetic problems. Dropping a ball or throwing it. Okay. So we could do ball flight using that acceleration, using g, so 9.8 if we were being specific, or about 10 if we were estimating from some of our examples, as the A in our kinematics problems from last chapter. That was one of 2 things that we did with little g, the 9.8 meters per second squared. What was the other thing we did with little g? That didn't actually involve a kinematics equation. There we go. We also used it F equals ma to get specific. So weight equals mass times gravitational acceleration. And we use that as though we were falling, even when we're not. Even when we're just standing still, it might seem odd. Okay, now, everything that we did was 9.8, or maybe we rounded to 10, but still, we're talking about 9.8. And that's true if we're standing here in Chicago. It would be true if we went to, say, Hawaii. It would be true if we were in China or India, right? It doesn't matter. I go down to the basement. I go up to the 2nd floor. It's just G, 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 G. Now, where would I need to be that it actually isn't little g? It isn't 9.8. Talk to each other for a second.
Any place. Pluto.
A black hole. It's not 9.8, guys.
Spaceship in space. On Pluto.
The sun.
So anywhere else but the planet Earth. Yes, I like the sun.
Or something
Do you
with
think
like
like
the exact same mass, like gravity.
True, because like space is a lot pretty large. There might be another.
I'm gonna go with space for now.
Huh?
Let's go for space for now.
I liked the sun.
The sun
Yeah.
stands on the sun.
What's that possible? It is if it's at night.
I've heard that before.
Okay.
We need to watch that show.
So where would I go that it isn't little g? It isn't 9.8 meters per second squared. Lucian.
Somewhere farther away.
Okay. How far do I have to go? Could I go up on the mountain? Yeah. If I went up on top of Everest, assuming I didn't die, and assuming I left with me some sensitive
You think that
equipment,
could
could
be
I
effective
measure
crafty?
a difference in G? Yeah. It'd be really tiny. I wouldn't notice it. I wouldn't feel like lighter or heavier or anything. But if I did a really sensitive experiment on top of average and just begin to measure, like 5 decimal places or something, and I can measure a difference. But where would I go that it would be appreciable, that I would feel different?
The
Space.
sun.
How about like the International Space Station? Would I feel different there? Okay. Well, that's kind of weird. Because don't we see pictures of like people floating in there, like swimming after M&Ms and chips? Everything seems to be
But you can't
floating.
swim
And
in
yet,
it. That's a-
Tyrone is saying, it's still about 90%. We have to come to grips with that. Now, let's look at Earth's radius. We'll get to that. We're not going to talk about our orbit just yet. All right, so here we go. How big is the Earth's radius? Does anybody have that number? Number 6, 10 meters. When you're crazy, that's less than 1. All right, so we accept the number 6,370 kilometers. But in our calculations, we tend to use meters. So let's be careful. We'll write that 6,370,000. I'm going to round it off. 6,400,000 roughly. Now, any idea how far out the shuttle, the shuttle used to go to the space station. So when we're talking about a shuttle flight or a space station, any idea how far out we have got to go to be in orbit? Sorry? Miles. That's only 400 kilometers. That seems rather close. But let's do that. That is correct. So we take our 64 and we'll add another 4 to it. So there's our 400 kilometers. That's 400,000 meters. And we'll put our space station there. Our shuttle has to fly there, assuming it has to be mission, because it's been doing this a while. We're still flying up to it. But let's say we're at 400 kilometers, 400,000. We're essentially above a significant amount of gas, so we're not totally out of the atmosphere, but it's so thin up there that it's not going to cause any problems. It's not going to be at the station. That's going to affect the orbit. But Tyrone is suggesting that we still have most of that pull on us. We still have most 90% of that gravitation acceleration, that little g. It would be about 9. And yet we see people floating like it's 0. So before class is over, we have to come to grips with that. But right now, we need a way to calculate what that reduction would be. Did you have a question or clarification?
No, I just wanted this
He mentioned an idea. I'll let you be next, but I want to hold that off till we calculate exactly how much little g, called little g prime, is. Is it closer to 0 or is it closer to 9, as you suggested? So
Are we going to do that with our weight in that?
it's all kind of tied together, right? Once we come up with an effective g there, call it little g prime, that would be what our weight technically would be there. Now, it might be difficult for reasons that he suggested, and maybe Alex is going to say, dude, to actually make that measurement. But technically, we would still have weight. If little g is 0. So, we need a formula that's going to talk about how stronger or weaker gravitation gets with distance. First off, are we getting stronger or weaker as we go away? So we're going to have something about the distance in the so I'll put it as d. And now the question is, how strongly does it fall off? Is this to the first power, to the second Does anybody know what it is? Tyro? There we go. This is an inverse square law. It's one of several that you might learn. It's the only one that we will do in this class. So that means if I were to go out twice as far, if I take this distance here, Earth's radius, and I double it, and so now the number here is twice as big, and I square it. How much weaker should gravity be? Should be 1/4. So out here, at one more Earth radius. So if this is Earth's radius, add another Earth radius, and we are at 1/4. So if g on the surface was about 10, out here, little g should be about 2.5. And you can see we're in, if it was about 10 here, Tyrone seems to be right. We seem to be a lot closer to being 10 than 2.5. But we want to find that number exactly. So, besides distance, making gravitation weak, what should affect how strong it is? What should go in the numerator? What does it depend on? Rob?
Could it be the mass of the two objects?
There you go. So we're going to take your mass, call it the space station or the astronaut or whatever. What would be the other mass? What's attracting it?
M1 or G.
Okay. In this case, it would be the Earth, right? So the Earth and the object being attracted. And now we need a constant because all our units are made up. We made up what a kilogram is. We made up what a meter is. But physically, there's a relationship between those atoms, that distance, and the force that we feel. Now, does anybody have an idea how big or small that number is? Big number or small number? Small. Really, really small. You know how you know it's really, really small? That's true. But again, our units are made up, so that constant still could be a big number. This is, let's see if I can recall it. 6.67 times 10 to the minus 11. And you know this how, Bert, that it's small.
If the mass of the Earth is huge, and we don't experience like such a vast amount of downward gravitation, so I guess it's small.
That's pretty reasonable. What about right now? Are you attracted to me?
Not that much.
For a whole variety of reasons, right? I should have clarified gravitation.
That's
You know?
not that.
I don't, yeah, of course. So, I'm 100 kilograms, right? Let's say in a few years you'll be 100 kilograms too, all right? The product of that, that's 10,000, right? 10,000 in the numerator, and we're separated by 1 meter. Certainly not 10,000 newtons, right? In fact, Bert feels absolutely nothing, thankfully. All right. So, that says G has to be really, 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 really tiny, but not zero, right? You get something as massive as the Earth, and now that product is equal. All right. So just how massive is the Earth? Well, that's a pretty big number. That's 5.97 times 10 to the 24th kilograms. Wow. I think of that as like 10 moles worth of kilograms. All right, now this distance, if we were on the surface of the Earth, if we're on the surface of the Earth, we're putting in Earth's radius, right? I want to know, say, what the force is on me standing here on the Earth. Okay, so I'll put in 6.4 times 10 to the, what's that, plus 6. And that's meters. So now this is meters squared. We have kilograms times kilograms. Can anybody figure out what kind of units I need to put on this in order to get units of force back? So it'll be easy. We'll cheat. We'll say newtons per. Tell me what it needs to be per to get me newtons back. And then we'll get the number. First figure out. Okay, so if I divide by kilograms squared and I multiply by meters squared, now it all works out. Meters squared divided by meters squared goes away. Kilograms squared divided by kilograms goes away, and I'm left with this. All right, so not an easy thing to remember, but you could do just like I did to recreate it perhaps on a test. All right, take out your calculator. Oh, by the way, I said unfortunately, I'm about 100 kilograms. Go ahead and calculate what my weight in newtons should be.
Do you have a calculator?
I need it about 100 kilograms. You would need it, right? Or if you were given the weight, you could solve for it. Oh? Did you put me on a diet? How much do I weigh? Yeah. Oh, you forgot the square. So. I'm like
I think I may have did this wrong.
I could be my own planet. I could be Minor Planet 25538. You guys ever heard of it? Minor planet, dwarf planet, asteroid 25538. Take a moment to look that up.
I swear to gosh, if it's Pluto.
Nope, this is in the main asteroid belt between Mars and Jupiter. Look it up, 25538.
I swear to God, if it is
Yeah, I'm an asteroid. I think she's calculated my weight because I'm like 3 kilometers. No, I've been waiting for a picture. I haven't rated a mission.
Oh my God. Oh my God.
All I can say is they were really running low on names to give up at that point.
Oh my God. Wait. This is a
So, what is my
2, 5, 5, 3.
units?
That's him.
Yeah, my force. If the force was with me, what would it be?
Wait, what's M2? What's M2?
The second one.
No, but I mean, like, what's the number?
100.
Maybe it's a rounding issue. Maybe I should have left that as 37. But you can see, I'm very, very close to what? I'm very close to 9.8 times 100 here. So basically, if you take off the second, mass, basically, you've calculated little g. Right? So at the surface of the Earth, this should work out to be 9.8. She got 9.73 again, I think, because I rounded here. But so why is it useful to do this instead of calculate the force? Because we want to know how much weaker it's getting here. But of course, the force will depend on what object we put there. You put the space station there, you get one value. You put U there, you get another value. You put a minor planet, dwarf planet there, you get a different value. But you want to know that basic 1/4. You want to know that little g is 1/4 what it was here. And so that's why we typically are going to calculate what's in the balloon and leave this off. and we're going to call this the gravitational field strength.
Do you keep getting
And
like a
if you
really
took
big number
something
that
over
starts with
newtons
6?
and you divide it
keep
by
getting this
one of the
number.
masses,
Yes.
you'll have newtons per kilogram. That means for every kilogram I put there, it weighs this many newtons. I put twice as much there, of course it will weigh twice as much. What's in the balloon? It's almost all of universal gravitation except for leaving off this mass. So I'll write it for you again, Emily. We'll say it's the force per mass 2. And that equals G mass 1 over the distance between them squared. We're going to call it the field strength. The newtons per kilogram at that. Now, we still want to get back to here. And just to see if the number in my head is at all close to Tyrone's, let's be careful. Let's use now, instead of 6.4, use 6.37. Let's see how precisely we can get this. I want to know what is little g, we'll call it little g prime here, where the International Space Station or some of those ships are going to need it. What is the field strength of little g prime at that point? So, you need to be careful. You've got this distance plus that distance. So you have to add those up when we stick it in there, and then remember the square. Does Earth mass change? Does a constant change? Nope. So all you have to do is adjust that number, and you should be able to get little g. We'll see if Tyrone is close. Yes? We're not worried about that. We're wanting field strength. We want to know how strong the pull would be on any kilogram put at that location. Do well. So I'm wanting the gravitational field strength at the altitude of the space station. You should get a number, and the units you should put it on would be newtons per kilogram. It should be a number less than 9.8. It should be a number greater than 2.5. And we want to see how close we get to Tyrone's suggestion to be around 9. Technically, I think he was suggesting 8.9. Still. No, it sounds like computation. Everyone else right? Josh, do you have another? Okay. How about start kicking on the calculator? Otherwise, we'll start scanning a meter later. Vincent, how are you doing? Yes. In terms of this, I trust you can handle everything else. I'm worried about the physics right now. And I think you can handle it too. How are you guys doing?
Good. Okay.
If I open it up till 11 p.m. tonight?
Yes.
Okay.
Thank you.
Wayne, how are you doing? You're still worried about being hurt? Did you understand how she calculated the 973 for me? You took and plugged in these 4 numbers. This here, line mass there, and the radius of the Earth there, and squared it. you would get her 90. Okay. But now I want you to leave this off. You want to do field strength, this, and this. And now that hasn't changed. The earth didn't change. The constant didn't change. The distance, though, did, because we have to add to this. Again, we'll use the more precise value. We need to add to that this distance here. Put that sum in here and square it, and now you should get that field strength, that little g prime. And we expect it to be between 9.8 and 2.5. In fact, we expect it to be a lot closer to 9.8.
What is E?
Huh?
What is E?
E?
Yes.
Like the value of it?
Yes.
Isn't it like twice pi? Oh no, it's not. It's like 2 point something, I think.
Okay, 2.718.
So interestingly, it's the same number. You can think of it as newtons per kilogram, or you can think of it in the old way as meters per second squared. I think conceptually this makes more sense, but they're the same thing, same number. Just two different ways to consider it. What did you get? 8.69. All right. Is that what everybody gets? Timothy, you're nodding yes? All right. Now, go ahead and divide that just for fun. Since he gave it to us a fraction or a percentage, what does that work out to be? Split the difference. I had 88 in my head, he had 90, and there was almost 89. All right. Pretty good. So now that's a little wacky, right? I mean, it makes sense. If this is 2.5 and this is 9.8, that looks like it. 88 or 8.69 seems reasonable. If that's the case, a 10% reduction in your weight, maybe if you were hopping around, I mean, you see on the moon, they hop around, they have like 1/6 their weight. But here we still have 90%. I wonder if we could actually feel it. In experiments where they put, sort of physiological, psychological experiments where they put weights in your hand, typically you have to have a factor of 2 difference before you're confident that you know what's in your hand is actually a different amount. So I'm wondering if we would sense weight being reduced 10%. But the videos we see, people are just swimming, they're floating. So that's kind of kooky. That doesn't look like 90%. So we have to come to grips with that. Tyrone has an idea, Alex has an idea, but I want you to talk to the people at your table. See if you can make sense of that.
So would that mean? Would it be if like a person is underwater, would the gravitational force still be the same?
Yes, but that's the whole buoyancy thing.
But she said,
I don't know.
what's the question?
So in the space station, people are still like 90% of the weight, so it seems like that they shouldn't be able to do like the floating and stuff that you see them do. So why can they do that?
They're really skinny.
Because maybe it's because I remember in his situation about if you're on the top of Mount Everest and it would only change by like a couple of decimals, so you wouldn't feel it as much.
Right.
So it would take a lot more to change the whole gravitational force.
Yeah, but that's
So even if it's so even by that small amount, you would feel such a different change. No.
no, because they could like do all the floating and stuff.
All right, Lucian, tell me what's going on. We have 90% of our pull, our weight, in orbit. And yet it looks like we have none. It looks like we have 0. It looks like we're floating. We're swimming through space, pushing off, gobbling, floating through space.
Attraction.
What's the explanation?
you're falling, but you're falling around the Earth.
Okay.
So,
So we're in free fall, but we never get there. Okay. That's absolutely right.
Wow.
Did you guys catch that? We are falling. We're in free fall, just like that marker was. But we never get to where we're going because we're going really fast that direction. Basically, if I was stationary here in 1 second at the surface of the Earth, how fast did I travel in 1 second? In 1 second. Start at 0, end at 10. My average was, I did it for how long? How far should I fall? 5 meters. So in 1 second, if you just push me off the building here, I fall 5 meters. Okay. Now, if let's say you don't just topple me, you shove me. Okay. So now I'm going to do this, right? And in that 1 second, I fall 5 meters. I've gone a ways that way. Now you say, oh, that's not good enough. It's put me in a cannon.
Oh my. Me. Oh.
Now, if you fire me fast enough, such that in my time traveling here in 1 second, by 5 meters, I've gone far enough in the curvature of the Earth. The Earth has dropped away 5 meters. I fell, but I didn't get any closer to the Earth. So as long as we get to that really, really high magic speed, anything less, I'll eventually hit the Earth. Anything more, and I'll eventually go off into interstellar space, perhaps. Maybe another good direction for me. But at what we call the orbital speed for this altitude, which happens to be about 8 kilometers per second, it'd be like going from here to, it's 8 kilometers away. That's kind of halfway between downtown Aurora and like Fox Valley Mall. So, but you go that far in 1 second, and the ground has fallen away about 5 meters. And you could be in orbit if you didn't splatter into buildings and trees or burn up in the atmosphere. You could indeed be in orbit. And Tyra, who was drawing that way back when? Famous person. If there was a cannon that fired fast enough that cannonball could indeed be in orbit and come and wonk you on the back of the head. Sorry? Okay. So, does that kind of make sense? We're falling, but just like being in an elevator here, we don't have the sense of that weight. We don't have the sense of that pull. We just are falling, and we're just never getting to the Earth because we have to be circling really fast. Now, at space station altitude, you know how, what that speed is, how fast we go around the Earth?
9 minutes.
Yep, about an hour and a half. Okay, so at shuttle orbit, space station orbit, ISS, takes about 90 minutes. How long does it take the moon to go around the Earth? Now, is there a sweet spot somewhere between 90 minutes and 28 days that'd be a nice spot to say, oh, put a satellite? Talk about that. What do you suppose geostationary orbit means and what it looks like? Talk to each other.
Let's see.
I'm guessing it's about
Is it just like how far you have to go to not move?
To not be pulled away.
Yeah.
I think so. What? There's an orbital period the same as the Earth's rotation. so it's like the definition of a satellite.
Where would be a good spot to put a satellite?
In my butt.
Where would you put it and why? What might you use satellite for? Let's say, you're going to do a one-man solo sailing trip around the world. And you'd like to tell somebody if your boat is upside down and filling with water and maybe come get you. Do you have a satellite phone? How do you know that you would get reception? Do we have to put like 1,000 satellites in orbit to make sure wherever you are, you will get coverage? We'll keep it simple. I want to communicate with the satellite here in Chicago all day long. And I want to do it as cheaply as possible. I'd like to do it with just one satellite. How would I do it?
Well, you put it in orbit, stay with the Earth.
So I'm looking for the spot. What are we looking for?
Sorry. 24 hours.
In the neighborhood of 24 hours. Okay. In the neighborhood. Because the idea, if it takes a day to go around, the Earth will have rotated and I'll still see that as overhead. I don't need to have a whole series of different ones. Okay. So the sweet spot is at about 6.5, 6.7 Earth radii, I think. So if you ever go and have a look at a map of things in orbit, you're going to see this band of there's hardly any room for anything. You just see this incredible mass of communication satellites at that distance. Then we got a handful of only flying over the poles, kind of interesting stuff. But mostly we're just trying to mount signals, and it's getting pretty jam-packed. All right, now, all right.
Well, I don't know what you're talking about. GPS is middle of the different.
Okay.
They're like 16 hours.
So you could get by with just a couple. You couldn't get by with one.
Yeah, the single ones you take the GPS station or
Right, and you have to take into account what's your frame of reference in terms of what the period is. Is it the stars or the Earth? Yeah, we won't worry about that, but in the neighborhood, the period. All right, now, let's say we wanted to calculate little g for the Earth. Way out there at the moon's distance. And I tell you to do it on a test. And I don't tell you what the mass of the Earth is. I don't tell you what the mass of the moon is. But I tell you the distance to the moon is approximately 60 Earth radii. Could you give me a value? This sounds like a level 3 problem. Could you give me a value or a ratio for what little g way out there is compared to the surface of the Earth? Talk to each other for a second.
Well, I don't know.
So I am interested, maybe the easiest way to say is, what is the ratio of little g way out there compared to little g at the surface? Is there a slick way? And you wouldn't need to know the Earth's mass. You wouldn't need to know the moon's mass. You wouldn't even need to know the universal gravitation constant. I'm saying you should be able to get to it just with knowing the distance to the moon in relation to the Earth. Is that the space jump? Yeah, it kind of. All right, who's got an idea? Ron? All right.
So, we know that the gravitational field strength on Earth is 9.8.
Okay.
And then we also know that that is with 1 Earth radius
Okay.
in the denominator. Now we have 60 Earth radii in the denominator.
So we'll say the field strength of the surface, the field strength out of the moon. And now you were saying we know at the surface this is 1 over Earth radius squared. And we know out of the moon it would be what?
1 over 60 Earth radius
60 Earth radii squared. Now, I said you didn't need to know all this other junk. Why not? What am I missing in the equation for the field strength? Okay, mass of the Earth. We have it there, mass of the Earth here. What else?
Big G.
Big G. Now, why is it we don't need those? Eunice says they cancel, and indeed they do. So the only thing that changes is now the denominator of the denominator. I'll take it up here, right?
So it'd be,
Or what?
so it'd just be Earth radius squared.
Yeah, I wrote the inverse another way, but we'll go ahead and do this. 60 Earth radii, and now we'll square everything. So 60 squared, r squared. Now we're going to cancel those. And we're left with this ratio is 3,600. And I wrote it as the surface over the moon. I should have done the inverse, but let's do that. We'll say field strength out of the moon compared to the field strength on Earth is 3,600. So very, very weak, but not zero, right? The moon still needs to fall around the Earth, as it were. And so if we wanted to turn that into a number, then we could say little g, if this ratio is 3,600, we could say little g prime equals our g at the surface, 9.8, divided by 3,600. Go ahead and turn the crank. See just how small that number is. So that's newtons per kilogram or meters per second squared. Jack, you get that number?
No.
Can you get that? Do you understand the logic of what we did?
A little bit.
Okay. So, how are you? Where did you leave it?
Okay, so you have the ratio and the
I only need to know what changed. And the only thing that changed is the distance. And I'm given that as a multiple of the other. So, here was my formula. The only thing changing is v. And I'm told that at the moon, we're basically 60 Earth radii compared to when we're standing on the surface, and we're 1 Earth radii. So if we take the ratio, all those ugly things that we have to look up or be given go away, provided we're told how far away the moon is in relation to the Earth's radius. Given that, it cooks down to this simple ratio, and then I can go back and say, remember the field strength? That was just another name for our acceleration constant. So this ratio here, I can rearrange and get a value since I know this was 9.8 on the surface. This is the Earth pulling on the moon. This would be if I take something that's not moving here and let it start to accelerate towards here. Okay. I'm not talking about a person here in some sort of competition between Earth I'm just saying, any object in this location will feel the field strength of the Earth in relation to this ratio. Okay? Now, put the moon there, and we would need to take and multiply this tiny, tiny number by the huge mass of the moon. And now we would have a big number. So you might ask, which is pulling harder? Does the Earth pull harder on the moon, or the moon pull harder on the Earth, or are they the same?
They're the same.
I hear equal. Why?
Because Newton's laws.
Sorry?
It goes back to forces.
Newton's third law. And you can look at our equation, right? It wouldn't matter if you flip M1 and M2, multiplication doesn't care the order. So the force would be equal between them. But that, you couldn't say that little g prime for the moon was that number. That wouldn't work. So, anyway, get comfortable with this. It might take you working some of those problems in Quest. It might take you going through your notes, but at this point, we should get busy, do some of the other things, get at least the data for our ball toss. Then if you need to work on test corrections, I recommend that, given the retake is Monday. Remember, you've got that practice Quest posted. And before we meet again, you've got a Quest and due on Friday. Question? Yeah, you should know. You guys can get to work? Yes. Yep.
So,
What's happening? Homeschooling.